Hi everyone, in this lesson we're going to look at section 2.5. We're going to look at the equilibrium constant, KEQ. And some goals for today is that we're going to explain what KEQ represents, and we're going to write KEQ expressions for equilibrium reactions. And then finally, we're going to go through what factors affect KEQ, just like we looked at what factors affected rates of reactions, what factors affected equilibrium shifts. We're going to look at factors that affect KEQ as well. So first, what we're going to look at is what is KEQ. If we write down KEQ here, you may recognize some things from maybe physics class, for example, or what we've been speaking of previously. This K always represents a constant. So with our K, we often see constants like constants in physics class, constants in chemistry class. Our constant is going to be affected by things like temperature. And then the EQ is just short for equilibrium. When we talk about KEQs in chemistry class, or equilibrium constants, our equilibrium constants are going to be approximately equal to the concentration of products over our concentration of reactants. So it's a ratio. And we know that at equilibrium, what's equal at equilibrium is the rate of the forward reaction and the rate of the reverse reaction. We know that the concentration of products and the concentration of reactants is not necessarily equal at all, but the rate that they're forming and being used up, that is what is actually equal. And so our equilibrium constant is going to show us the ratio of those products to reactants. And you'll notice that I used an approximately equal to. We're going to be talking about some of the factors that affect this reaction and how it's not exactly equal to products over reactants, but some of that changes based on coefficients and what products and reactants there are. So, some rules when we are writing our KEQ expressions. I'm going to give an example of a reaction here. So we're going to start with hydrogen and oxygen transitioning into water. So you're going to notice that I have two H2s, and this is a gas, plus O2 gas. And you'll notice when they're in their gaseous form, H2 and O2 are diatomic, so we always find them in twos. And when we put those two together, we have this equilibrium reaction where they will form two molecules of gaseous water, H2O. Okay, so our first rule for writing the KEQ expression is that KEQ is going to be equal to our products over reactants. So I'm going to put our products, concentration of water, over the concentration of our reactants, H2, multiplied by that concentration of O2. But the coefficients become powers in this reaction. So you'll notice that I've got a coefficient of 2 for my hydrogen gas. That coefficient is going to become a power in the KEQ expression. This 2 for the water, similarly, is going to become a power. So we're going to show that that's the concentration of water squared divided by the concentration of hydrogen squared multiplied by the concentration of oxygen. That's equal to our KEQ. So that's the first rule for writing KEQ expressions. We've got one more rule that we're going to work with here. And the second rule states that only aqueous and gaseous species are going to be used in the KEQ expression. And that's because solids and liquids have a constant concentration. So that concentration doesn't change at all throughout the equation. So here's an example of that. If I had calcium hydroxide, for example, calcium hydroxide is a base, but it's also solid. So when we have calcium hydroxide by itself, we get this solid calcium hydroxide, and we're going to show that that's in equilibrium. When we put that in water, that's going to split apart into its ions. And the calcium ion is going to dissolve in water, and we're going to get two hydroxides as well that are going to dissolve in water, and they're aqueous. So when we write a KEQ expression for this reaction, we're going to put our products over reactants, but this time we're going to leave out the reactants because they're solid. And again, just like our last rule, that coefficient becomes a power in my final equation there. So my KEQ expression is KEQ is equal to the concentration of calcium ions multiplied by the concentration of hydroxide ions. And because I've got a solid over on the left-hand side, on the reactant side over here, I'm going to leave it out of the expression, or alternatively, I could put everything over 1. Same thing here. So there's our KEQ expressions. So we're going to practice this together. If you can get out your notebooks, we're going to try this on page 120 in your workbooks here. We're going to do a quick check. So it's going to have you write the equilibrium expressions for the following reactions. So what I'll have you do is to pause this video for a few seconds, give everybody a chance to go through questions 1 through 4, and then you can unpause the video as I go through the answers to these questions. Okay, answer to question number 1. You'll notice that with this question, we've got 2 gases on the left-hand side of the equation, on the reactant side. On the right-hand side, I have a solid, so I'm just going to put a line through that, just reminding myself to leave it out of my equilibrium expression. KEQ for this one is going to be the products, so the H2O, and I'm going to take that to the 3rd power, divided by the concentration of B2H6, multiplied by the concentration of O2, and again, I've got a coefficient of 3, so I'm going to raise that to the 3rd power. So there's the answer for the first one there. Second one, you can see that we've got all gases, so all of those gases are going to be included in my equilibrium expression. KEQ is equal to, I'm going to do Cl2 squared multiplied by H2O squared. Now, if the H2O, if this was a liquid, I would leave it out, but because it's a gas, it can change its concentration, so we'll leave it in the equilibrium expression. I'm going to do HCl to the 4th power on the bottom, and oxygen just to the 1st power, or just leave it by itself. So there's for question number 2. And I'm kind of running out of room here, so I'm going to just change colors here for the 3rd one. We're going to look at hydrogen and bromine going together. Now the bromine, this is a liquid, so I'm going to leave this out of the expression. So the 3rd one here, this is going to kind of line up down here, is equal to HBr squared divided by H2. Okay, and that's it for that 3rd question. Last question, I'll do it here in green. Again, I've got a solid, and this is the one that I did in my practice here. So KEQ is equal to the concentration of calcium ions. You'll notice that the charges just get left. Don't leave those charges out either. Those are really, really important, and we're going to be talking about how those charges are useful for tracking where electrons go later on in the units. But make sure you just leave those and copy those charges exactly as they are and put them into the equilibrium expression. So there we have it for the first 4 quick check problems. Now, the equilibrium expression can give us a little bit of information about the extent of the reaction, about whether that reaction took place and went close to completion, or whether that reaction didn't go very far at all, it didn't move much. Remember that because these are equilibrium reactions, that does mean that we probably have our entropy and our enthalpy kind of facing in opposite directions. So with these ones, probably the tendency towards enthalpy is maybe going to the product side, and the tendency towards entropy is going towards the reactant side. At any rate, we've got this equilibrium because of those 2 opposing forces. So the value of KEQ can tell us a little bit about the extent of the reaction as well. If we have a very large KEQ, for example, that means that the reaction favors the formation of the products. So I'm just going to put a couple notes in here about what the value of KEQ tells us. If KEQ is very large, now, if you look at that fraction, if it's very large, that means we have to have a lot of products and not a lot of reactants. This means the reaction favors the formation of the products. If, on the other hand, if KEQ is very small, and we're going to see some of those when we look at acid-base equilibrium and solubility as well, if KEQ is very small, that means that the reaction favors formation of the reactants. And then finally, there's only one other scenario, but if KEQ is equal to 1, that means that the concentrations of the reactants and the products is about equal. And that's very rare to get a KEQ of 1. Okay, so that's what the value of KEQ can tell us about the extent of that reaction. So if you see KEQ values, and you're going to see a lot of questions that kind of state the KEQ, and they'll say KEQ is equal to, let's say, 6.7 times 10 to the negative 13. KEQs don't have units, by the way. The units don't tell us that much. So you'll notice that KEQ, we always leave off the units. But this number is very, very small. So that will tell us that the reaction really favors the formation of the reactants. We've got far more reactants than we do products to force that ratio down. Okay, looking at factors that affect the KEQ, just like reaction rates, just like factors that are affecting our equilibrium, we have factors that affect KEQ. And in this case, it's a little bit easier to remember than some of the others because the only thing that affects KEQ is temperature. So if you want to take a look through your data booklets, for example, there are a lot of different KEQ values written in your data booklets. There's some KEQs specifically for solubility. There's KEQs for acid-base equilibrium. You'll notice that all of those have a temperature value listed, and the KEQ for each of those scenarios is only good at that specific temperature. And in your data booklets, it's assuming it's at 25 degrees Celsius. That's kind of our standard temperature for that. So the only thing that affects KEQ is temperature, but if you were to change the temperature, then your KEQ is messed up and you won't be able to use that same one. So pay attention to the experimental conditions, because if your KEQ is the same in 2 experiments, it means that that ratio is going to be equal. Okay, so we're going to look at how that temperature affects KEQ in an endothermic reaction or an exothermic reaction. So for this one, for example, if we increase the temperature in an endothermic reaction, if we increase the temperature, what happens to KEQ? So if we increase the temperature, what we'll notice is that that heat value is going to go up and equilibrium is going to shift to try and decrease the heat. So what we're going to get is we're going to get a right shift. Now, what a right shift means is that our reverse reaction is our forward reaction is faster than our reverse reaction for a little bit. That means we're going to be making more products. And we're going to be consuming more of the reactants, so we're going to be using up the reactants. So if you'll remember that KEQ is products over reactants, if we have more products being made and fewer reactants being made, that means our KEQ value is going to increase. So if you increase temperature with an endothermic reaction, KEQ also increases. Now, with an exothermic reaction, that should be the opposite. If we increase the temperature, that's going to cause a left shift. And if we get a left shift, we're going to get more reactants made, more of the stuff on the left, and we're going to have fewer products. That's going to cause our KEQ value to decrease. So depending on whether you have an exothermic or an endothermic reaction, it has the opposite effect when we raise the temperature up. Okay, now we're going to get into a little bit of the math. We're going to talk about calculating KEQ. So in this example, at 25 degrees Celsius, now you'll notice that it gives us a 25 degrees Celsius, but this is a piece of information that you're not going to need to use in your calculation. It's just kind of a piece of information to tell you that that KEQ that we calculate is only for 25 degrees Celsius. So it says that solid calcium hydroxide is in equilibrium with its dissolved ions. So I'm going to start this problem. We want to calculate KEQ. I'm going to start this problem by writing out the equilibrium equation for what happens when calcium hydroxide dissolves. So I'm going to start with solid calcium hydroxide. Okay, so my equation for calcium hydroxide is CaOH2. If you didn't know that that's the equation for, or that's the formula for calcium hydroxide, go back again to our periodic table. You'll notice that calcium is an alkaline earth metal, and alkaline earth metals tend to donate 2 electrons, and so they take on a positive 2 charge. With hydroxide, hydroxide is a polyatomic ion, and if you don't remember the charge for hydroxide, you can actually look it up on your table. And if you look it up in your green booklets there, your data booklets, I think it's on about the 3rd page of the data booklets, you'll notice that it has a -1 charge. So we've got positive 2 charge, -1 charge. If we kind of swap and drop, you'll notice that we need 2 hydroxides for every 1 calcium for that formula to be balanced. So it's in equilibrium in this equation with its dissolved ions. That means that the water is actually going to break this ionic compound down into its ions. So it's going to dissolve in water, and that calcium is going to split apart from the 2 hydroxide ions. So there's our balanced chemical formula. From this balanced chemical formula, now we're going to write our KEQ expression. So we're going to leave out the solid, and we're going to do products over reactants. So I'm going to put my calcium with the 2+ charge on top. I'm going to put the hydroxide next. And remember that our coefficient becomes a power. And over reactants, we can put this over 1 or just leave it how it is. So now that I've got the formula there, I'm going to fill in the results from my question. So it says that the concentration of calcium ions is 2.1 moles per liter. Concentration of hydroxide is 2.8 times 10 to the -10 moles per liter. And I'm going to square that. Now I'm going to put it in my calculator and calculate KEQ. So I'm going to take 2.1 multiplied by 2.8 times 10 to the -10, and I'm going to square that. I get KEQ is equal to 1.6 times 10 to the -19. Now you'll notice with this one, I've got no units. You're also going to notice that when I write this out, I write 1.6 times 10 to the -19. I don't want to see anything like 1.6 e -19, nothing like that, okay, please? So 1.6 times 10 to the -19, we're going to put this in proper scientific notation form. And the other thing we want to check for is the appropriate number of sig figs. So in the question, I have 2 sig figs from my calcium. I've got 2 sig figs as well from the hydroxide. So I'm going to round this KEQ value to 2 sig figs as well. And that's all there is to it for calculating KEQ. Okay, we're going to try the next one. This one is a KEQ problem, and this time you'll notice that they're giving us a KEQ value, and it's giving me a KEQ of 1.7 times 10 to the second power at 225 degrees Celsius. Now again, the temperature isn't something that we're going to be using in our equation. It's just that we can only use that KEQ if the experimental conditions are also at 225 degrees Celsius. So we're going to double check that. Now it says a slight variation on this type of problem. You could be asked to determine an equilibrium concentration from the KEQ and from the other equilibrium concentrations. So for this one, we're going to start out the problem by writing out our KEQ expression. We've got the balanced chemical equation because it's been given to us. So we're going to do products over reactants. So we're going to take NH3, that ammonia squared, divided by concentration of nitrogen, multiplied by the concentration of hydrogen, this time to the third power. Okay, so those coefficients are becoming the powers. Now this equilibrium actually happens to be the Haber reaction. So this is for synthesis of ammonia in a commercial setting. And this is one of the most important chemical equilibriums that we've had in the, in the 21st century. So, or in the 20th century. We're going to be investigating this reaction a lot more in the coming week or two. But for right now, we're just going to fill in all of the results that we know. It says, what is the equilibrium concentration of H2? So for this particular reaction, we're going to want to rearrange our formula to solve for H2. And we can rearrange at the start or we can rearrange at the finish. Doesn't matter when we do it. But I'm going to suggest that if you're planning on going into something like a pure math or pure physics or pure chemistry or engineering, it's usually beneficial to rearrange for that concentration of hydrogen right now before we plug in our values, because often things will end up canceling out when we go to do things later on. So I'm going to do the little switch thing that we talked about in the first week of class, where I bring the hydrogen up to the numerator and the KEQ down to the denominator. So I'm going to take H2 cubed is equal to NH3 squared over concentration of N2 multiplied by my KEQ. Now, next step I'm going to do is I want to get rid of this cubed with the hydrogen, so I'm going to cube root everything on both sides of the equation. And then, last thing, I'm going to solve for H2. So my concentration of H2 is equal to the cube root of NH3 squared multiplied by N2 times KEQ. Now, when you're putting everything in your calculator, also remember that everything underneath the in the denominator there, everything needs to be in brackets. So I'm going to put a little multiply sign there. And also remember that that cube root applies to everything on the right-hand side as well. So when we're entering it into our calculators, we're going to be really cognizant of the bracketing. So I'm going to go ahead and I'm going to substitute all the values in now. So my concentration of NH3 is 0.14 squared. On the denominator side, I've got a concentration of 0.020 for the nitrogen concentration, and the KEQ is given down below 1.7 times 10 to the second. And I'm going to just put a set of brackets there for good measure. I'm going to put everything into my calculator, and I'm going to finally round to 2 sig figs at the end there. So I get a concentration of hydrogen at 0.18 moles per liter. And you'll notice that this time I do have units because I am talking about a concentration here. I'm not talking about a KEQ. Concentrations have units, and it's a capital M, or you could put 0.18 moles per liter. That's also correct. Either one of those would be fine. If you left it in scientific notation, that would be great as well. Okay, so pause the video here if you need to. Please make sure that every single person in the class can do this on their calculators. Make sure that the bracketing is working. And if you are not getting the proper answer, if you're not getting that 0.18, ask a partner. See if somebody else with the same calculator can help you with the brackets as well. Or put a star beside it and ask me when you see me again in class, because I want to make sure everybody can use their calculators at the same time. Okay, moving on to the last little bit of this lesson, looking at trial KEQs. So sometimes we're going to be looking to try and predict which way equilibrium will shift if we start with a certain concentration and seeing whether the reaction is going to shift left or right to achieve equilibrium. We can try that by plugging in initial concentrations. That's concentrations where we're not at equilibrium. We can plug those into the KEQ equation and then compare the trial KEQ value to the actual KEQ value. So kind of the rule here is that if my trial KEQ is less than the KEQ, it means that we're going to have a right shift. We're going to shift towards the product side because we're going to try and move that trial KEQ value so that it matches the KEQ. If the trial KEQ is less than KEQ, it means we need to make more products so that we balance it out and we move to that KEQ value. If my trial KEQ is equal to the KEQ, then my system is in equilibrium already. There's going to be no shift. And finally, if my trial KEQ is greater than the KEQ, this means that we have too many products. So the system is going to shift to the left-hand side so that we can use up those products and we can convert them to reactants. And that's going to take that trial KEQ down a bit, and it's going to make it balance it out and be equivalent to the KEQ. So that's how we can use our equilibrium constants and a trial KEQ to predict which way equilibrium will shift. So I've got one example of that problem. It says the following gases are introduced into a closed flask. Okay, so we've got this closed flask. We've got 0.057 moles per liter of sulfur dioxide, 0.057 moles per liter of oxygen, and 0.12 moles per liter of sulfur trioxide. And it says, in which direction will the reaction proceed to establish equilibrium? So it says we're introducing these gases to a closed flask. That means that these gases are not at equilibrium. At least they're probably not. So we're going to calculate a trial KEQ. And our trial KEQ is the same as a KEQ. We're going to take our products over reactants. So I've got SO3, we're going to square that, divided by SO2 squared multiplied by O2. So I'm going to substitute everything into this expression. I got my SO3, 0.12, we're going to square it. On the bottom, SO2, 0.057 squared. And then my moles of oxygen, 0.057 again. When I put this in my calculator, I'm going to double bracket this whole bottom part so that we remember that the denominator consists of all these things. And I'll put them into my calculator. Trial KEQ is equal to 77.76. Okay, it's a few too many sig figs. Trial KEQ 78 is good right there. Now, what we want to do is compare that value to the actual KEQ. You'll notice that 78 is less than 85. So my trial KEQ is less than KEQ. So I'm thinking back. The only way to make that trial KEQ bigger so that it matches the KEQ is we need to make more products and less reactants. And the way to make more products and less reactants is to have a scenario where my forward reaction is greater than the reverse reaction for a little while. And we get that by having a right shift. So my final answer is when those gases are introduced to a closed flask, the reaction is going to proceed to the right to establish equilibrium. All right, that's it for the lesson for today. So for today, I'd like you to go through and read the pages in your workbook that are related to KEQ. I think that's on page 115 to 121. And then you can try the practice problems as well in your workbooks on pages 125 to 128. If you get those finished, you can go kind of back and work on some of the problems from our entropy and enthalpy section as well. I want to have a short quiz on that tomorrow, just to make sure that everybody's on the right track, and remind you to study some of this stuff before the end of the unit as well. So that's it for KEQ, and good luck with the problems.